So, when you picture a super advanced robot, what comes to mind? Probably all the amazing things it can do, right? But what if? What if the real secret to making them tougher, more resilient, isn't about what they do right, but about how they handle things when they go wrong? This new research digs into a really cool idea: teaching robots not just how to walk, but how to fall gracefully. I mean, let's be honest, humanoid robots are incredible feats of engineering. They're unbelievably complex and powerful, but that complexity also makes them, well, kind of fragile. A single locked joint, a wonky sensor, any little mechanical failure can send them toppling over. Because, they stand on two legs just like us. So falling is a huge, constant risk. And that really brings us to the core question here. It's not just about trying to prevent every single fall. That's probably impossible. It's about what happens next. How do you give a robot the reflexes to save itself when a fall is already in motion? How do you teach an AI to improvise under that kind of pressure? Well, according to these researchers, the answer isn't about finding one single perfect way to recover. No, the idea is way more ambitious. It's to build a massive library of options, a whole toolkit of reflexes the robot can pull from in the blink of an eye. Just think about it for a second. If you stumble, you don't have just one move to catch yourself, right? You might throw out a hand, or take a weird quick step, or maybe you'll grab onto something nearby. The goal here is pretty much the same for the robot: to discover a huge diversity of successful recovery moves, not just one, for every single situation it could possibly find itself. So, how do you even begin to build a library that big? Well, the researchers came up with a new algorithm. It's got a bit of a mouthful of a name, MTMB Map Elites, but its secret sauce is actually really elegant. It works by cleverly smashing two powerful existing ideas together. Let's use an analogy, because it makes this way easier to grasp. Imagine you've got one single locked door. That door is one specific problem, like recovering from one specific type of leg failure. The first algorithm, Map Elites, is kind of like a master locksmith who's obsessed with finding every possible key that can open that one door. The whole point is getting a huge variety of solutions, but just for that one task. Now let's switch it up. Imagine you have a whole hallway full of different locked doors. That's a bunch of different problems. The second algorithm, Multitask Map Elites, is different. It's trying to find one single, reliable master key that can open as many of those different doors as possible. Its focus is on finding one solid solution that works across many tasks. So you see the difference, right? It's really crucial. On one side, you've got Map Elites going deep on one problem to find tons of unique solutions. On the other side, Multitask Map Elites is going broad, trying to find one solution that works for many problems. Both are really useful, but neither one is the whole picture. And this is the breakthrough. The new algorithm combines the best of both. Instead of just getting lots of keys for one door, or one key for lots of doors, it finds a full-on key ring packed with different, unique keys for every single door it comes across. It's all about having the maximum number of options for every single problem. Okay, so the theory sounds pretty smart, right? But does it actually work? To find out, the researchers put their new algorithm to the ultimate test, a high-stakes simulation with the Talos humanoid robot. And here's where it gets really interesting in how they defined a task. For every single time the robot's leg failed, the algorithm had to explore two different ways to solve it. One task was to try and recover using only its right hand against a wall. The second task was to try it again, but this time using both hands. The process itself was a simple but absolutely brutal loop. Step 1, a random fault gets triggered in the robot's leg, making it unstable. Step 2, the algorithm makes the robot try to plant its hand or hands on a nearby wall. And step 3, the simulation just watches for 10 seconds. If the robot is still standing after that, success. And they didn't just do this a handful of times. Oh no. To really prove their method was the best, they ran a staggering 25,000 simulations, and they pitted their new algorithm against 3 other methods, including things like a random search and a more traditional grid search. So the big question is, after all that work, did the new algorithm actually win? Did it come out on top? Well, let's dive into the data and see what it says. So the first thing we gotta look at is just raw performance. Could it solve the problem? As you can see from this chart, the new method, MTMB, Map App Elites, solved nearly 68% of the recovery tasks thrown at it. Now, that's a whole 10 percentage points higher than the next best alternative. That's not just a little better, that's a decisive win. But hold on, because remember, just solving the problem wasn't the main event here. The real goal, the big ambition, was to build that massive library of options. It was never about finding an answer, it was about finding all the answers. And that brings us to the most jaw-dropping result of the entire study, which we can basically sum up with this one single number, 2x. So what does that 2x even mean? It means that for every single problem it managed to solve, the new algorithm found more than double the number of unique, effective recovery strategies compared to any other method they tested. So it wasn't just better at solving the problem, it was exponentially better at finding a rich, deep, diverse set of solutions. It actually built that reflex library. Okay, so why should we care? Why does building a huge library of ways to fall gracefully actually matter? Well, because this research points toward a future with fundamentally smarter and way more adaptable robots. You see, this method isn't just some one-off trick. It's a whole new way to generate incredibly rich data that shows all the possible ways to succeed at a task. You can then take that data and use it to train much more robust, more resilient AIs, helping them avoid that classic trap of just learning a single brittle solution that breaks easily. In fact, the authors themselves see this as a powerful alternative to more common AI training methods like reinforcement learning. They point out that those other methods often don't explore enough. They find one good way to do something and just stick to it, which can be really fragile. This approach, on the other hand, is all about exploration. And all of this leaves us with a final, really interesting question to think about. As we keep building more and more advanced AI, what does robust really mean? Is it an AI that has one single perfect master plan? Or is it an AI that, kind of like us, has a whole library of possibilities to choose from when things inevitably go wrong? This research makes a really strong case that the library is the way to go.